Welcome and thank you for standing by. At this time, all participants are in a listen-only mode until the question and answer session of today's conference. At that time, you may press star 1 on your phone to ask a question. I would like to inform all parties that today's conference is being recorded. If you have any objections, you may disconnect at this time.
Thank you and hello. I'm Laura Betts from NASA's Office of Communications. The team is gathered today to talk about early science results from the agency's James Webb Space Telescope. The agency will live stream the audio of the teleconference on the website. During today's expert availability, you'll hear more about distant galaxy research and what this means to the team with us today. We'll then be taking media questions. Here to give us an update on this research is Tomasa True, Principal Investigator for the GLASS JWST Early Release Science Program and Professor at UCLA, Elena Henry, GLASS JWST Co-Investigator and Webb Instrument Scientist at the Space Telescope Science Institute, Jehan Kartalatupe, Co-Investigator for the Cosmic Evolution Early Release Science Survey and Associate Professor at RIT, Doris Illingworth, co-investigator for the first reionization epoch spectroscopic complete and public release imaging for extragalactic research galaxy surveys and professor at UC Santa Cruz, and Jane Rigby, Webb Operations Project Scientist from NASA's Goddard Space Flight Center. So let's get started. Tell us about the results that we just shared, Tomasa.
Well, thanks. So the first conference I attended as a first-year graduate student 24 years ago was entitled Scientific Drivers for the Next Generation Space Telescope, which of course eventually was named JWST. And to tell you the truth, in those 24 years, the thing I've been looking forward to the most was a surprise, something unexpected. Because, as scientists, when we discover the unexpected, we really are learning something new about the universe. And this is why I chose for the GLASS JWST program the title, An Exploration of Galaxy Formation and Evolution. I meant it to be a way for the astronomical community to get a quick look at what surprises the universe had prepared for us. And the universe and JWST did not let us down. As soon as we started taking data, we discovered that there are many more luminous distant galaxies than we had been expecting. Somehow, The universe has managed to form galaxies faster and earlier than we thought. Just a few 100 million years after the Big Bang, there are already lots of galaxies. JWST has opened up a new frontier, bringing us closer to understanding how it all began. And we have just started to explore it.
Thanks for that. And what do you feel like we're learning here, Elena? Elena, are you unmuted?
Now I am. Sorry. So I wanted to say that GLASS is a really great survey and doing really neat stuff, and for a number of reasons. One, it's using gravitational lensing, so we are targeting a large galaxy cluster in the relatively local universe, and it is magnifying the sources that are behind it so that we can see fainter and more distant galaxies. But the thing that really gets me excited about GLASS is that it's not just taking images, it's also using it's also using spectrographs on Webb to get more precise information about the galaxies that we want to study in the early universe. And so for the first galaxies, when we disperse the light with Webb into its different colors, it's like using a prism, and we are able to see the fingerprints of the different atomic elements that land at different that have different colors in the spectrum of the galaxy. So we get much more detailed information about the contents of galaxies, the rates that they're forming stars, and the motions of the gas. This really gives us a much more precise and higher fidelity picture of the galaxies in the early universe, the first galaxies that ever formed. And one of the cool things also is that spectroscopy really is just giving us the most incontrovertible measure of the distance or the redshift to the galaxy. It's telling us how long that light has been traveling to us, where the galaxies are in the early universe. And it's allowing us to do this at a way that confirms that the things that we see in the images really are at higher redshift. And Webb has just been finding and confirming these things left and right. It's been really exciting and really amazing.
Thank you. I appreciate that. And Garth, could you tell us how does this fit into what we've learned so far with other projects?
Yeah, thanks, Laura. Yeah, it's clear, and as the other two speakers have already emphasized, that we're seeing and revealing amazing insights into the early universe and to galaxies in the universe. And this is really realizing the promise that we saw several decades ago when we were working in JWST, the Next Generation Space Telescope. It was the sort of formative years of Webb, of JWST. When the first Hubble Deep Field was revealed in 1995, we realized that there was such a universe of galaxies to explore that any images, any pictures of the universe were going to reveal a dramatic number of galaxies. And we realized that Webb, NGST at that time, would be the telescope to really tell us about those, to reveal them and to let us study them at the very earliest times. And NGST really then set the stage for the study. This activity was done in 1997 when a wonderful volume was put together with concepts for NGST, one of which was eventually developed into Webb. And that was called Visiting a Time When Galaxies Were Young. It was a very prescient study, I think, focused on the galaxies at the earliest times. Now, if we jump forward now for almost 25 years from those very earliest days, we can see that we're really on track to realizing the dream of understanding galaxies at the earliest times. And with the last few months have been exciting, but a huge amount remains in front of us to learn and to gain insights into what is really happening in the first billion years of galaxies.
Thanks for that, Garth. And Jehan, what exactly is SEERS and what does this mean for you?
Hi, so SEERS is the Cosmic Evolution Early Release Science Survey. And so this is a program designed to study galaxies in the very early universe. But more than that, it's meant to test out the various observing modes of JWST, including obtaining both imaging and spectroscopy at the same time. So the science goals of SEERS really has two major themes. One is to investigate the first light of galaxies that brought the early universe out of the dark ages. And the second is to study the subsequent evolution of galaxies and their growth over cosmic time. The one thing that really struck me in the early days of JWST images is how quickly our understanding of galaxies is changing. So to put myself back in my shoes in July, watching that initial press release, I was awed by the fact that we were witnessing a once-in-a-generation moment where just overnight our capabilities and understanding of the universe were about to change.
Wonderful. Thank you very much. Now, Jane, can you tell us just how Webb's doing so far?
Sure. Good morning. So today's briefing is all about these results on high redshift galaxies, but I can provide some larger scale context. So JWST is in our 5th month of science operations. We are full steam ahead for science. And JWST has been a gift that has taken months to unwrap, and the result was that almost across the board, the observatory is more powerful than our pre-launch expectations. The images are sharper, the pointing and guiding are more stable, we have darker skies, darker backgrounds, and greater, better sensitivity. We've documented all that performance, and yesterday we put out our call for proposals for the 2nd year of science. Every day we're plowing ahead with science operations. We're observing new targets, we put new data in the archive. We've delivered our on-orbit calibrations for all the instrument modes. So calibrating with real data from space, which we're refining throughout the year. And the results we'll talk about today are just some of the flood of new discoveries that are pouring in just as we hoped.
Thank you, Jane. We'll now be taking media questions. Please remember to hit *1 to unmute yourself during the question. Operator, we're ready for the first question.
Our first question comes from Marcia Dunn from AP.
Yes, good morning. I have a question about the galaxies being discussed in the research papers being presented today. I'm wondering, so the galaxy that's 350 million years post-Big Bang, is that now the farthest galaxy identified to date through any means, the oldest light, so to speak? And how long will it take to confirm that, and how quickly do you expect to find more record breakers? And again, I also know that if I could also touch on one more thing, you're saying that stars are forming earlier than thought. How much earlier, and compared to what you thought before Webb? Thanks.
Amisa, would you like to take that?
Sorry, this is Garth Illingworth. Did you ask me about that? I wasn't sure. I didn't hear the name very well.
Oh, yeah. Go ahead, Garth.
Yeah, certainly. I could say something, and others certainly could too. So this is a very dynamic time. There have been lots of preliminary announcements of even earlier galaxies, and we're still trying to sort out, I think, as a community, which ones of those are likely to be real. We feel very confident about these two, but less confident about the others. So there's certainly a lot of discussion going on, and there'll be more results as the data improves and as the processing and calibration also improve from the telescope. So, and the other part of the question, so I think, it's TBD. Let's see how this develops over the next few months. And I fully expect we will find some even more distant galaxies, even at earlier times, that we will feel confident are real galaxies. So the second part about the early star formation, this is amazing. We are seeing such bright, such luminous galaxies at early times that we are really uncertain about what is happening here. that trying to build up a big, massive galaxy within hundreds of millions of years is an incredible challenge. And so we are wondering, do we really understand the early phases of the formation of these galaxies? And so I think this has posed a lot of questions for the theorists for trying to understand galaxy formation, and it will really be a lot, as Elena has mentioned, will depend a lot on the spectroscopy too, into revealing insights into what these galaxies are like. So anyway, others could maybe comment on this as well. So thank you.
Would anyone else like to comment as well?
Yeah, this is Tommaso Treo. For example, for the galaxy, the most distant galaxy we're talking about here, there's been a tentative confirmation with ALMA that has shown a line which is consistent with oxygen coming from this line. There's no detection of dust in any way. These galaxies are extremely blue, which is the other puzzle that we're facing. Not only the universe seems to be able to form stars very quickly, but whereas in the local universe, usually star formation is associated with dust and they tend to be dust enshrouded, these galaxies seem to be extremely blue and unobstructed by dust. And I think what we're starting to see now is the James Webb incredible capabilities to confirm them spectroscopically. We're hoping this one galaxy will be confirmed soon. There have been a few reports of other galaxies at slightly lower redshift confirmed spectroscopically up to redshift 10, which is the second most distant one here. But really, everything, as Garth said, everything is changing rapidly, and every day we're learning something new. So this is an exciting time.
Thank you. Ready for the next media question?
Our next question comes from Nell Greenfield-Boyce from NPR.
Hi there. Can you guys hear me okay?
Yes.
Hi. Thanks for this. Thanks for doing this call. I had a question sort of along the same lines that Marcia just asked. I want to make sure I understand. So I know that you guys are not interested in record holders. You're interested in, groups of galaxies so that you can get a sense of, comparing them all and understanding what the populations were like. But if I do mention a record holder, I want to make sure I get it right, if that makes sense to you. So could you help me understand this one that you all are mentioned, which I think is what Tommaso just referred to? There's one 350 million years ago, after the Big Bang, sorry, not ago, after the Big Bang. Is that spectroscopically, confirmed? Is that, totally solid or no? What's the oldest one now that you guys feel is, totally, totally solid? I'm sorry if this is not an elegantly asked question, but, I understand it's early days and people are putting out lots of candidates, but, what's the one where you're yep, this is, the oldest one that we know for sure? Thank you.
So if I can take this one, Tommaso, just to follow up, maybe it wasn't clear enough. So I think this one is extremely solid, the one at redshift 12. It's been confirmed independently photometrically by 4 or 5 different teams. So that's a good example of the experimental method that works. And then there is this tentative confirmation with ALMA. So I think this is as solid as it gets at this point without JWST confirmation. I don't think there's anything more solid at higher redshift so far.
That's the one that's 350 million years after the Big Bang.
Right, the redshift 12 one.
Yeah. Oh, okay, and may I ask one follow-up then? I understand that it's fluxing times, but of the various candidates that people have put forward for ones that might go even farther back, are there any that look particularly tantalizing, or is it all just like a big mess at this point? Who knows for sure?
Let me just add a quick comment to that. Hi, Nell. This is Garth Illingworth. So I think that these are tantalizing. There were some early papers submitted on a galaxy which was even around 250 million years after the Big Bang. But there's quite a lot of uncertainty about that, and it actually could be mimicking a much later galaxy at around 1 billion years. That's one of our great challenges here, is that galaxies at later times can sometimes mimic these very early galaxies. And so we desperately need better data, but also the confirmation data, the spectroscopy. ALMA, as Tommaso mentioned, is a great source of getting the information on these. So we're waiting to see which of these ones at earlier times turn out to be real. And as I said, I think probably there will be, given how bright the one at 12 is at redshift 12, 315 million years. But we really don't know at this stage. There's none that I think any of us in the community would be confident about.
Thanks so much.
All right, next question.
Our next question comes from Issam Ahmed from AFP.
Hi, thank you for taking my question. Actually, I had a few, so I'll see how many you can do right now, or you need to come back to me. In terms of the most distance, it's glass Z12. What changed from the preprint? Because I remember covering that, and we talked about a redshift of 13 at that time, and I guess that changed. And could you sort of explain why the measurement changed? Obviously, it's still thought to be the most distant starlight. And also, if we could, I think maybe Tommaso alluded to this at the start of the call, but the biggest takeaway for what this means in terms of our understanding of the early universe, and could you sort of draw that out a little bit for us? What these findings together sort of nudge you towards or point you towards? Yeah, and then I think you already answered the sort of another question about what separates certain and uncertain observations, because you have a lot which are uncertain, and I think Garth was just talking about how that could be to do with mimicry. If you can maybe expand about on how later galaxies sometimes mimic earlier, that would be interesting. Sorry, that's a lot.
Elena, would you like to take that question?
So there were quite a lot of questions there. So let me see if I can start with the last one for sure. I have some experience with the later galaxies mimicking earlier galaxies, and so we pick these galaxies out of images based on what colors they have. If they are, when we look at them in the optical, in the visible wavelengths that we see with our eyes, they drop out, and then we see them showing up in the infrared with JWST or previously with HST. And one of the things that can happen is if there is a lot of dust, or if the stars are just really old, it can block out that optical light. The dust can block the optical light, or the galaxy might just be really red. And sometimes those things, if they're dropping out because of those features, then we might make a mistake. But there are ways to tell the difference based on how much light you're seeing at the different colors in the infrared when we are looking. If the spectrum if the light from the source is then relatively blue, looking like young stars, in the rest, when we look at in the infrared with JWST, then you can kind of tell the difference between an old population at low redshift, or a dusty population at low redshift, and a early universe first galaxy. And so if the sources are fainter, then that can be a little more challenging. But so that's why we sometimes have a challenge. But really, getting a spectrum of the source, when we look we see emission lines from different elements, it really tells us exactly what we're looking at. So that's kind of the gold standard that we need to head towards. I don't remember what the other parts of the question.
So why did the redshift for the most distant shift from 13 to 12.5?
So someone can correct me if I'm wrong, but I think it is because some of the calibration on the NIRCam data may have just been updated because the first calibration was very, very preliminary, and it's just been getting better and getting more and more precise. And so I think that's what happened. If that is incorrect, someone can.
Yeah, can I jump in for a second? I think part of the reason why there's this question is that we are talking about photometric redshifts based on imaging that have an uncertainty. And so when we first measured this, it was somewhere between 12 and 13. I think it was like 12.5 or 20.6. And I think the two independent teams that reported first sort of chose to round off the numbers. One of them referred to 12, one of them referred to 13. So there was like a rounding effect. And so I think we shouldn't be distracted by that. It's somewhere between 12 and 13, and we will know precisely exactly where it is when we get the spectroscopic confirmation. ALMA says 12.1. If that holds up, that's the redshift, but I think we really need to see a JWST spectrum to know precisely exactly what the redshift is. We know it has to be somewhere between 12 and 13, but we cannot be more precise than that until we have a JWST spectrum.
Yeah, thanks. And the final one was the sort of broadest takeaway of these findings taken together. How do they shift our understanding of the early universe, or what do they how does the hypotheses sort of shift now?
Jehan, would you like to take that?
Yes, if I understood the question correctly, it's how do these discoveries shape our understanding of the early universe? And I think there's a bit of a surprise element to this for everybody in that the very first discoveries came so quickly and they were relatively bright. We all had our estimates based on cosmological models of how many of these really high redshift galaxies we'd be able to find. And we thought it would take a while to really build up a population at these redshifts. So it's been a bit of a surprise that there are so many that formed so early. And that is posing a challenge to how galaxies formed early on in the universe. So it's exciting for us, from a theoretical standpoint, that maybe there are some open questions about how these galaxies could have formed their stars so much earlier that we're able to detect large numbers of them. And it also opens up an exciting window, for future observations of just how many of these sources we'll be able to study.
Thank you.
Thank you. Next question.
Our next question comes from Alexandra Wise from Nature Magazine.
Hi, my questions are for Tommaso. Number one, what constellation is the glass field of view in? And secondly, do you have follow-up observations scheduled for spectroscopic confirmation of the Z13, either on JWST or elsewhere? Do you have time actually scheduled for spectroscopic follow-up?
Okay, so I'll take the second one first because it's easier. The constellations are not in my forte, but I'll look it up. Sorry about that. We have submitted a proposal to the Space Telescope Science Institute to use what is called director's discretionary time to confirm that. And so we're waiting for their answer. So we don't have any JWST time scheduled. The next opportunity will be on cycle 2 if it doesn't get awarded now. We think it's urgent enough to warrant an earlier confirmation, but that's the path, right, to get JWST spectra. So at the moment, there's only ALMA tentative lines. From the ground, it's impossible. It's just too hard. We've tried with lots of ground-based telescopes. It's just too hard. So it has to be JWST. And for the constellation, I'll look it up in a second.
It's Sculptor.
Oh, okay, sorry.
Thank you, James.
Thank you.
All right, next question.
Our next question comes from Bill Harwood from CBS News.
Yeah, hi guys. Can you remind us what the record holder is for HST? I mean, just to get a sense of how much further Webb is kind of pushing. And then a related question, maybe this is for Garth, how would a JWST deep field fit into this, or would it not? I mean, based on the nature of the observations you're trying to make with gravitational lensing and all that. I'm just curious how a deep field with Webb would work with this. Thanks.
Yeah, this is Gareth the Linguist. So actually I was part of the team that did have the record holder on Hubble. And that was a galaxy at redshift 11, about 400 billion years after the Big Bang. And that was one that had some spectroscopic confirmation as well. So that was a huge surprise at the time. And I think one of the things that has in many ways added to the surprise is that we are finding galaxies like this so readily with Webb. So this is this whole question about how galaxies are built up over time. And so let me then also, deep field is absolutely great to have, with Hubble, the Hubble Ultra Deep Field, the Hubble Deep Field, and all the various manifestations of those with different cameras that have really given us a huge amount of insight into galaxies in the early universe. And in fact, Webb has a deep field that is coming up in the next few months. It's going to be done on the Hubble Ultra Deep Field too. So there will be deep fields done in Webb as well, and hopefully several of them, so we get a good coverage around the sky.
Yeah, can I squeeze in just one more quick one?
Go for it.
Yeah. Is there a theoretical limit, or I should say, is there a guesstimate based on what you're learning as to how early stars could have formed? I mean, you think about hundreds of millions of years, it's hard to get a grip on that. But I mean, what's the latest guesstimate on when a star could have formed for the first time? Or is there even a guesstimate? I guess that's the best way to put it.
Yeah, well, I'm sort of laughing because this has got to be a great topic at the moment, because finding these really bright galaxies has opened up the whole ball game. So I think anything earlier than 100 million years would just be really weird. And I think we were mostly thinking a couple of 100 million years was likely to be where the very first things formed. But these galaxies are potentially so massive that it may push us back earlier than that 200 million years. But this is really a great open question at the moment. When did the first stars form? And so these galaxies, I think, will be a pathfinder to that, and the deep fields, because we need to look at fainter galaxies as well and understand what they are like. So, there's some great work coming up with Webb in probing those early years, just as we hoped when we started this telescope decades ago. It's realizing the dream that we had then in a fascinating way.
Thanks a lot.
Let's take our next question.
Megan Bartels from space.com.
Hey there, can you hear me all right?
Yep, coming in clear.
Wonderful, thank you. I just had a follow-up question in terms of waiting for spectral confirmations from JWST. Is there any reason that those weren't taken at the same time as the data you have now? And is there any concern about sort of validating a telescope's observation with other observations from the same telescope? Thanks.
Thank you. Great question for Jane.
All right. So to back up the context a little bit, what we've been talking about here is taking images that cover, big images covering, you see, with thousands of galaxies, and then finding those objects that have the most exciting colors, right? And in detail, looking at their colors from imaging and saying, ooh, those are what I'm looking for. It's true for a number of things that we do, including finding these very high redshift galaxy candidates. And then the natural progression is the spectroscopy. And in fact, JWST has 4 science instruments. All of them have spectroscopic capabilities for exactly this reason, this power of spectroscopy for both knowing how far away something is, like precisely, not being fooled by these sorts of what did one of the previous callers, the mimicry. So spectroscopy gives you an unambiguous distance and thus a look back time, but it also tells you what stuff is made of, and which is super important. So that progress of let's find the most interesting candidates and then let's follow them up was built into the design of the telescope. That's why we have spectroscopic capabilities on all 4 science instruments. It was just baked into the plan. And so your question about your question about reliability, it would be using different instruments or different observing modes of the same telescope, which have very different capabilities. But that sort of process of we find the candidates and then we do spectroscopic follow-up, that's been the plan all along. It also takes some time, right? So what we're at, for the beginning of that process of finding things with fascinating colors, doing everything we can with the imaging, and at the same time getting ready the spectroscopic follow-up.
Got it. Thank you.
Thank you. Next question.
Jonathan O'Callaghan from Scientific American.
Hello, thank you for taking my question. Nice to speak to quite a few of you again. Yeah, I've got a first question for Jehan. I know you're part of a follow-up team that's looking at a few high redshift Sears candidates that just got some DDT time. Could you talk through what that program is going to be doing? And then could someone explain what the possible redshift limit is for JWST? I've seen some estimates of a redshift of 26, maybe even further. What is the furthest you think you could see a galaxy or a proto-galaxy? Thank you.
Okay, so for the first question, for the DDT time that we have coming up, this is to follow up a few different candidates that are in one of the Sears fields that were found early on. And so this is from one paper, by Finkelstein et al., but also includes some candidates in some other papers that multiple people have found. So it's about 3 or 4 different very high redshift candidates that will be followed up. And so those observations are supposed to take place, toward the end of November. So we're using the near spec instruments and trying to get spectroscopy of them. These are very, very faint. So we will see, if we're able to detect them, but if so, we might be able to confirm some redshift. For the second question, others may jump in here, but I don't know if we really know what the theoretical limit is. I think we would have given you a very different answer 6 months ago than we might today. Redshift, 20, is kind of a pretty high upper limit. Detecting galaxies there would be very difficult. You have to imagine, right, the bright galaxies we're seeing are kind of the tips of the iceberg, are the things that are bright enough that they're peeking up that we're able to see them. Of course, there are many other galaxies that are fainter that we can't see. And some of these upcoming deep fields that were mentioned earlier may be able to probe even fainter. So I think that question remains to be seen.
Okay, thank you.
Thank you for that. Next question.
Daniel Cleary from Science Magazine.
Hello, can you hear me?
Yes, coming in through. Clear.
Right. Hi, thanks everyone. I wanted to ask, you talk about the unusual brightness of these galaxies and how that was a bit of a puzzle. Can you speculate a bit more on what might be the cause of galaxies becoming that bright so early on? How the process of formation and development could be accelerated. Also, how confident are you about that brightness? There were some issues early on, I understand, about calibration of the sensors on NearCam, and they were more sensitive than people were expecting. So how confident are you about this brightness of the galaxies?
Let's go to Jane for the calibration part.
Yeah, let me take the second part first. So calibration, just for what that means is taking the thing we measure, which is count rate on the detector, how many photons we measure, and translating that into a physical thing, how much power, how much energy per second comes down from the distant object that we're looking at, right? So that calibration can be done on the ground crudely, and it gets done better in space. And we knew all along that's the case. We have flux calibration built into the Cycle 1 science program. Initially, when we wanted to get data out to the community as early as possible, and that data was released with basically our best estimate of the calibration from the ground. And that's based in the lab, and there aren't very precise little lights in the doers in the lab, basically. We knew that, and we told everybody that. And then once we were in space, we calibrated the instruments from stars. For NIRCam, that's an extensive process because there are 10 detectors within NIRCam. Each one has to be individually calibrated. So you have to put the star on each of the 10 detectors. And further, you have a whole bunch of filters to do each color of light, each waveband. And so that was just a time-consuming process that we crunched through. And those calibrations got quite good in October. So that's what these papers are now using, but those are the most recent calibrations. That's not a surprise. It's partly due, as you said, because NIRCam is more sensitive than we expected. But it's just the normal work of getting a new observatory and dialing in the calibration. And I'll let someone else take the first half.
Yeah, let me address that. I mean, I think that this is an important point to clarify that, the calibrations we're talking about are at the 10, 20% level. So obviously, this is important for very high precision photometry. But these galaxies we're talking about, they're so bright, that even if you have the luminosity off by 10%, they still remain very bright. Okay, so if something costs like a lot of money, even if you have a 10% discount, it's still a lot of money. And the same is true for the colors, right? So these calibrations have changed the colors a little bit, but the colors of these high-energy galaxies are so obvious because basically every piece of light that comes below a certain wavelength just gets absorbed by the universe. That there's an extreme difference in color between two consecutive bands. And so that's an unmistakable signal that really does not depend on the calibration. And I think the teams knew early on that these are the things that you can do robustly even with preliminary calibration. And for more detailed work, we will have, we will have to wait for the better calibration. But those early results in terms of high-energy galaxies are robust in that sense.
Great, thank you very much.
Actually, can I add a little bit to the first part of your question, because the fascinating aspect of these. So these are very bright, as Tommaso and Jane emphasized, but they also, if we think of them as we think of later galaxies, we immediately jump to the conclusion that they're very massive. And that causes this real enigma. How did they build up so many stars so early? And so one of the issues that's now being widely discussed is there's something very different about these early galaxies. And one of the options could well be that these are really sort of what we've often called a population 3, the very earliest stars. And in fact, they are bright, but they're not very massive by comparison because they are really dominated by very bright stars. So this is opening up a whole question about the nature of stars and how they form and the type of stars that form in the very earliest times. And it's a very open question because we really need spectroscopy and getting JWST, ALMA data all together, these different telescopes will reveal whether these really are very different to galaxies at somewhat later times.
Great, thanks a lot.
Thank you. And we have one more question, so let's take that one, and then we'll need to wrap up. So what's the last question?
Our last question comes from Nancy Atkinson from Supercluster.
Hi, this is a kind of a general question for Jane Rigby, and if anyone else would like to chime in, I'd really appreciate it. Now that you've had 4 full months into the mission with an operational telescope, what are some of the highlights for you, both in terms of what the telescope has observed and in working with the various teams?
Sure. This is Jane. I'll take that. Highlights over the last couple months. My gosh. Personally, one would be the DART impact, where we watched the DART the DART mission on purpose plow into an asteroid and change its orbit. I was logged into the telemetry and watching that come down, and all you get is that we're guiding. The data comes in a couple hours later. But for me, that was really exciting because we worked so hard to get those observations to work. That asteroid was moving 3 times faster than our speed limit before launch, but we have increased our speed limit of how what's the fastest moving target we can track. So we were able to support that other NASA mission, and that felt really good. And it's neat. It's telling us about how asteroids are put together and about what we might do to protect ourselves from them. So that made my day. I think I'm also, just every day, the data are coming in. They're gorgeous. A highlight for me from the kinds of observations we're talking about today, which Garth alluded to, is that these galaxies we're talking about are bright, and so they were hiding just under the limits of what Hubble could do. They were right there waiting for us. We just had to go a little redder and go deeper than what Hubble could do. So that's a happy surprise that there's lots of these kinds of galaxies to study, and that, as we were talking about, that star formation may have kicked off earlier in the universe than we thought. As far as the teams, I'm also just surprised by how tractable and gorgeous the data have been. I expected to spend a lot more time with my own data and with others really struggling to get the data to behave, but they look really gorgeous, and we're already getting really sophisticated papers out of them. And then I think for the team, you asked about the teams, for me, this is just, it's great to see the joy and the excitement of the teams. As one of the people who commissioned the telescope, we were working hard to get this telescope to behave through up until July, and now the data are in the hands of the whole world, and it's lovely to see the joy and excitement of those teams, and to see the discoveries just come out. So that's exactly what we wanted to see. The teams are analyzing the data, churning out science, making discoveries, and then proposing follow-up discoveries to deepen our understanding.
This is Garth Illingworth. Can I add something to that too? I would like, Jane certainly covered it very well. But this is a special time. So most of the programs that have been carried out in the last few months have had fully public data sets. So the whole community could be involved in this. And this was a very deliberate decision taken for the work of an early committee called the James Webb Science Advisory Committee, and working with Space Telescope and NASA to try and set up public programs that were available for everybody to use. And I think this has been a dramatic demonstration of how these programs really can help involve the community and involve the public as well, media, everybody, in the excitement of a mission when the data sets are fully open. So these were the early release science programs, and I think it's been an astonishing success to have that very public data. As you probably know, most of the data that Webb takes, in fact, 3/4 of it, is not available universally to the science community and to the public for over a year. So this is a very different environment and a very exciting time, and I think a very involving time for the community and, of course, for the public then when these results are communicated via the media and social media.
Thank you. And thank you to our experts and for everyone joining us today for this expert availability. Please follow along for more mission features and blogs on our website, nasa.gov/web. And if you have any follow-up questions, please don't hesitate, reach out to us, and we'll tackle them. Have a great rest of your day.